step into the unknown and do something sometimes without knowing how the outcome will be.
There is nothing exciting about a safe bet or the middle of the road.
If you're not on the edge, you're taking up too much space.
Find the strength to overcome the challenges ahead.
There's an incredible human being left for you to discover once you reach the edge.
If you want to make a difference in life, be a scientist.
Good evening, ladies and gentlemen. May I please have your attention? We will commence our session soon. Good evening to everyone here with us and our audience online as well. I hope so far you had a great and inspiring time at WEP. And now, as we are almost coming to a conclusion, we will take our scientific curiosity to the very edge. We will look at the most enigmatic objects in the known universe. Today, we have the honor and the privilege of a whirlwind talk by Professor Feryal Ozel, who will talk about her quest to explore the black holes. Professor Ozel is the founding member of the Event Horizon Telescope Project, a collaboration of more than 300 scientists from 13 countries. In May 2022, fueled by her passion for astrophysics, she led Event Horizon Telescope's unveiling of the first image of the supermassive black hole located at the center of our Milky Way galaxy. Here to introduce our speaker today and moderate the session is the chair of WEP herself, Professor Derya Baran. As you know, the talk is 1 hour long, 15 minutes of Q&A. Please join me in welcoming on stage Professor Baran and our speaker, Professor Ozel. Thank you.
Good afternoon, everyone here in the auditorium and those joining us online. It is the penultimate day of WEP 2023. While I'm a little sad that we are nearing the end of this amazing 2 weeks, I am so pleased to be introducing our last keynote speaker, which is actually the first Turkish scientist attending to WEP. Her work epitomizes the theme of edge. She is one of the pioneers of black hole photography. Feryal Ozel is a Turkish-American astrophysicist born in Turkey. She is the chair and professor in the School of Physics at Georgia Institute of Technology. She received her degree in physics and applied mathematics from Columbia University and her master's from the Niels Bohr Institute, and her PhD from Harvard University in astrophysics in 2002 on the effects of the intense gravitational and magnetic fields of neutron stars. She was a NASA Hubble postdoctoral fellow and member at the Institute of Advanced Study at Princeton before joining the faculty at the University of Arizona, where she was a professor of astronomy and physics. Dr. Ozel is a fellow of the American Physical Society and was selected as the Science Academy of Turkey. If you think that's it, bear with me, there's more. In recognition of her work, Dr. Ozel was awarded the Maria Goeppert-Mayer Award from the American Physical Society and the Guggenheim Fellowship the Radcliffe Fellowship at Harvard University, a Miller Institute Visiting Professorship from the University of California in Berkeley, and with the ETH collaboration, the Breakthrough Prize in Physics, the Rossi Prize of the American Astronomical Society, a Diamond Achievement Award from the National Science Foundation, and many more. Dr. Ozel has taken on numerous leadership roles at the national and international level. She is the co-chair of NASA's Next Generation Mission Concept Study for the Lynx X-ray Observatory and has served for 3 years as the chair of NASA's Astrophysics Advisory Committee. As a founding member of the Event Horizon Telescope collaboration, she has served on the EHTA Science Council since 2016 and was the lead of the modeling workshop group for 3 years. In May 2022, as most of you might know, she announced the first black hole image in the Milky Way galaxy and its science result to the world. It is my immense pleasure to have Dr. Ozel here, and please welcome her to the stage.
Thank you so much, Daria, and thank you all for being here. How are you doing? Ready for some frontier pushing with black holes? Okay, I would like to take you on this journey that lasted about 20 years, because sometimes discoveries and getting to new frontiers of human knowledge take some time. I know you've listened to extremely interesting keynotes in this EDGE session this year, from the depths of the ocean to frontiers of what we can print with 3D. And I would like to take you to the far reaches of the universe, where we can image black holes, develop technology that's necessary to do it, build collaborations that is necessary to do it, something that's becoming more and more important, more and more core to how we do science now. And I would like to also tell you about the new physics that we learned from it. I'm not going to assume any knowledge of physics, but hopefully I will be able to lead you through what it is that we discovered by doing this experiment with imaging black holes. Since we're going to talk about black holes for half an hour to an hour, let's begin by looking at what they are. They are actually predictions of Einstein's theory of general relativity, which is the theory that we use to understand gravity, how gravitational attraction happens in the universe, here on Earth, around the sun, around other planets and stars, and everywhere in the universe. What this theory tells us is that gravity can be described as a geometry where light and matter, like you and me, follow certain paths around other matter. So what that tells us is that if we think of space and time as a fabric that is shown like this grid on the screen, and there is no mass to distort it, rays of light that you're seeing on the upper right-hand corner in those red would follow straight lines on this fabric of space and time. What happens when a very massive object like a black hole distorts this fabric? Well, black holes are unique in that they not only distort this fabric, but they do it to a point where even light, which is massless, goes in and cannot come back out. So black holes create a region of space where, as you can see, some of the light is trapped and other light is bent around it. So it's a mathematical prediction of Einstein's theory of relativity. But do they exist in nature? Do they really trap light? Do they form what we call this shadow, this darkness or donut hole, if you would like, at the center where light truly disappears from the visible universe that we are part of? Meaning any information that goes in, any kind of matter that falls in, becomes invisible to us as part of this dark center. That's what we were after. And I was a PhD student, just like most of you here, when I started thinking about what it would take to really image, find this frontier, this edge where light disappears, and get experimental verification that what this theory tells us is indeed what is happening out in the universe. Unfortunately or fortunately, there is no experiment we can set up in a lab where we create a black hole, we shine light on it, and ask ourselves, does it disappear? Is there a darkness formed at the center? So what we have to rely on are black holes in the universe where the light around them is generated by hot matter that is falling into it. So black holes being providing the strong gravitational pull matter from stars and gas clouds around them, and as this gas cloud falls towards the center in this whirlpool, what you see here is our rendition on supercomputers of what happens to it, what happens to the fluid, what happens to the chemistry of it, what happens to the physics of it, and the temperatures climb to such high numbers that the gas itself starts shining. So even though we can't do this in the lab, there is a natural setting in which there is light forming around black holes, and if we trace it all the way down to the center and understand its properties, then we can map it onto images that you see on the upper right-hand corner there, where if we turn our telescopes, we will be able to understand the mapping between what that image shows and what is happening around the black hole itself. So, as I said, I started thinking about this early on, and one question that my colleagues and I asked are, if this is true, what is the wavelength of light that we would need to carry out observations at so that we're not stopped by this gas cloud that is circling around the black hole? Our view isn't blocked by it. We need something where it's going to be transparent all the way down to the event horizon, that point of no return, so that that shadow, that absence of light, is revealed against the background. So some of the earliest calculations I've done was looking at changing the wavelength of observations. So something could be transparent in ultraviolet, but not let visible light through, or something could be transparent to infrared and not let ultraviolet through. So using computer simulations, that's what I looked at. And as you can see, if you change the wavelength from a centimeter to a millimeter, which is short wavelength radio, the center of the black hole suddenly appears in our view. Based on that, I wrote 2 papers with colleagues back in the year 2000 and 2001 that I wanted to show you, where we asked ourselves, okay, if this is the case, which black hole candidate that we know in the sky should we look at so that we can, and at the right wavelength, we can see the heart of the black hole appearing? So we wanted to ask, which black hole is big enough in the sky and has the right properties that would suddenly bring this new phenomenon into our view that we've never seen before as humans? And we identified 2 candidates. I don't want to go into the details of these plots, but what I wanted to show you are 2 names that are appearing. One you can see over there, SGR A star. That is short for Sagittarius A star. That is the black hole candidate at the center of our galaxy towards constellation Sagittarius. And the second name you will that you will see there at the bottom, which is where you want to be, this is a plot of how much we can resolve. Can we get all the way to the heart of the black hole? And that's M87. So we identified these, and then it took 2 decades to get to what we shared with the world this year. Now, I'll tell you a little bit more about Sagittarius A star. This is, of course, the Milky Way. We are in the northern hemisphere, so if you look on a clear night sky, this is what you see. And the second one, M87, that I mentioned to you, is towards the direction of the Virgo cluster, where that's the Virgo cluster there, the young girl in Latin, and you see the arms opening there. Now, in the center of those arms, far away from us, is an entire cluster of galaxies that we call the Virgo cluster, obviously, because it's towards the constellation Virgo. The second brightest galaxy in that cluster of galaxies is M87. It's the second brightest, but there is something very interesting about it that we've known for almost 100 years through basic astronomical observations. There are jets coming out of the heart of the galaxy. When you go to the center, there are these collimated, bright structures that are jutting out from the center. That was the first clue, that first indication that something very energetic is happening at the center, at the core of this galaxy. And that's what led to many observations over decades to determine whether it's a black hole and what its properties are. So with these two targets, we then spent, as I said, the next close to 2 decades putting together an array, putting together people, and putting together the scientific tools. And I will fast forward and tell you what that looks like, and then go back and talk about these 3 frontiers that we needed to push in a little bit more detail. So I'll show you a movie that we put together just prior to our announcement of the black hole image in May of 2022. That shows the worldwide array, this telescope, this global telescope array that we built, spanning the Earth from Mexico to the United States to Hawaii to Chile in the southern hemisphere. And we turned our telescopes, and at the same time, all of these telescopes observed the center of our galaxy through our disk, through these gas clouds that obscure our view, these energetic clouds, and these stars that we know exist and orbit around a dark object, too dark to be a normal star. And when we achieved the resolution that we needed for an object that is 26,000 light years away from us, this is the image that we obtained for the heart of our own galaxy, Milky Way. So the farthest high resolution, the highest resolution image that we've obtained, the first indication that black holes really contain that hole in the middle, along with the image of M87, the 2 times that we were able to do this observation and analyze the data. And what did we learn? I mean, the image obviously is an achievement of a collaboration over so many years, the hard work of so many people. But I also want to tell you, did we learn some physics that we didn't know? Or what is it that we are after by imaging black holes? So three themes. One is building the telescope array. What did it take? You don't suddenly turn on a key and perform these observations. So what did that take? I will start there. I mentioned to you that back in 2000 and 2001, we started thinking for the first time about what would it take to take a picture of a black hole? What wavelength would it need to be? Which sources would we look at? Are there candidates in the sky that are feasible? And even after we did all of that, the answer that we came up with was, yes, there are 2 black holes that are feasible for seeing this this shadow, this heart of darkness. And we chose the right wavelength, that millimeter wavelength. And even then, what we realized is that it would take a telescope the size of the entire Earth to get the resolution. Not just a small handheld camera, not just one big dish, not an array of dishes that are connected to one another, but a telescope the size of the Earth to get to that. So obviously that is not feasible. It's not technologically feasible. It's not financially feasible. So we did the next best thing, which is use a technique called interferometry in order to connect telescopes. I'm sure some of you use this in your own research here. There are many different ways of interfering light so that you get a crisper image or a different image than what you can do with a single dish. So what we did with this interferometry technique is virtually connect telescopes across the globe. One telescope with its dishes and its very precise clock. The precise clock really needs to record data 230 billion times a second with a time tag, so that when it talks to its sister telescope somewhere else on Earth that is looking at that distant black hole at the same time, obtaining the data at the same time, we can then take this time-tagged data, put it on supercomputers in order to match up every wavelength, that every peak and trough that came through, and match them up as if we observed it with a telescope that is the size of the Earth, the size of the separation between the two. So I'll tell you just a little bit more about this, because this is really the heart of what black hole imaging looked like. Let's say that our two telescopes are in the Atacama Desert in Chile and in Spain, which are two actual telescope locations in the Event Horizon Telescope Array. Think of it like notes. If it was music, this would be notes. But in an image, it's just information about one thing about that image that you're trying to put together. So on the right, we're going to look at what notes we're hearing if a single doublet of telescopes, a single pair of telescopes is looking at this distant image. Obviously, that's not an image, right? That's just a dot. So what can we do? Well, we rely on the rotation of the Earth, so that this is very much like a medical imaging, where I don't know if you've ever gotten a CAT scan or an MRI. You go into a machine and the machine rotates around you, taking images from all different directions. And the reason a CAT scan is called a CAT is computer-aided tomography. Computer-aided because all of those are then combined on a computer in order to give you the image of your organs or whatever you're interested in. This is mathematically extremely similar. We can't rotate stuff around the black hole, but you know what? The Earth rotates. So we rely on the rotation of the Earth to get one component after another as the Earth rotates to get a different look at the black hole and fill in this space with different pieces of information about that image. And then we take it to a supercomputer, combine it in order to get the combined image from that. Because this is the technique, of course, we need telescopes all around the Earth. And when we performed the 2017 observations, we had the headquarters where I was, and we had teams all around the Earth with operating these dishes so that we could obtain data at the same time for our two targets, Sagittarius A star and M87. I'll show you a couple telescopes that I particularly like, although each one on the array is impressive in its own right. This is the submillimeter telescope on Mount Graham. I was in Arizona for almost 20 years, so this was our backyard telescope, so to speak. and really beautiful seeing from that mountain. Another impressive one that my colleagues helped put together in terms of the instruments that went on it is the South Pole Telescope. This literally is in the South Pole, and the amount of effort that went into getting that hydrogen maser clock that we need for the precision and the right instruments there was really a decade of work. The trips to and from, just to take the instrumentation there, they have to happen over the South Pole summer, which is our winter, of course, and there's a very short window in which you can get all the equipment down there. My colleagues travel on these cargo planes. I don't mean they put the equipment there as cargo. I mean they travel as cargo inside the same cargo planes. And this is one of our graduate students, Junhan Kim. It is extremely important that there is also humor involved in this. You can see here he's in a penguin costume during the race around the world, which literally involves running in a circle around the geographic South Pole. It is around the world, technically. So anyway, we had a lot of fun. So, as I mentioned, we take these little bits and pieces of information from all of these telescopes and put it together. And this is what the best coverage looked like for Sagittarius A star, and that is what the best coverage looked like on another day for Sagittarius A star. Now, you might think, I don't know anything about this. I kind of get what you're saying about this tomography thing, this interferometry, but I want to assure you that there is something very simple that you can understand and walk away from here and say, I know how they did the black hole imaging. And next cocktail party or whatever, next party that you go to here, mocktail party, excuse me. You can say, I know why there is a hole in the center. So I'm going to walk you through that. Okay, let's take all of this data and gather it into one plot. That plot is here. Look on the right side. The y-axis here is a quantity called flux density. It's just how bright something is. And the x-axis here is the separation between the telescopes. So when you do this Fourier transform, or this tomography technique, you're not seeing the image directly, but you're seeing the information content of, if I have my sensors a particular distance apart, how bright does it look? And that's what you use to reconstruct the image. We saw this first, and we were incredibly excited. That moment in your career where you're like, it worked. And you're going to say, why? What did you see there that made you think that this entire observational campaign and entire theoretical work led you to the right answer? Well, what you're seeing here is a ringing pattern. For mathematicians or physicists in the audience, this is a Bessel function, but you don't need to know what it's called. It is a very particular up-down pattern that happens with a given separation. And that right there told us that we had gotten the right thing. The reason is that, I'll show you here. Let's say that we had a blob in the sky, shown in this red disk here. And that on the right now, I have, again, the same data, all in red, and I have this trial image as that green line over there. Is that a good fit to the data? Does the green curve describe the red data points? No, right? No, it's a pretty terrible fit. So, okay, it has the right ringing pattern, but clearly is not in the right place. So what can I do? Well, I can change the size of this. By changing the size, now I got that first part right? But notice what happened. It's now ringing too fast, even though the first minimum in those data points is right. It's not giving me the right shape. Why is that? Well, because I filled it. If I instead made a thin ring, it would have given me the right shape, okay? There's one more step. You're going to say that those of you with a keen eye are going to say, that's really still not a good fit. Well, it's because I assumed right now infinite resolution. But our telescopes don't have infinite resolution. I have the size of the Earth to contend with. As big as that is, it is not infinite. My farthest two telescopes are basically from the South Pole to the North Pole. So if I now degrade it to the resolution of the actual image, that's the fit, okay? So that's the data, and that is the reason why we're sure we saw a ring of light with a hole in the middle that corresponds to the shadow of the black hole that we were looking for. Okay? It is that, even though we did years of analyses on supercomputers, it is this simple. And that's why we felt confident going out and saying, we saw the image of the black hole. Okay, you saw all those penguin races that were clearly important to building the technology that was necessary. Building the collaboration was just as time-consuming, and as scientists, I think we are less trained on how to work with people than we are with machinery, with our lab benches, etc. And yet it is becoming a key part of what we do as scientists these days. I mean, I'll be honest with you, I don't know of anybody who goes into physics because they're good with working with people, right? That is not a career choice you make because you just love being around people. So you learn. You learn as you go, and this collaboration is different than, for example, the particle colliders in Europe at CERN, because there, of course, the workforce is very distributed, but at least the location is the same. So in order to do your work, you come to the same location, one facility, one center where all the data are gathered. In our case, the telescopes are distributed, the computing power is distributed, the funding is distributed, and the people are distributed. So over the years, we started from literally a handful of people thinking about this. And as we added more telescopes to the array, as we developed more data analysis techniques, more theoretical modeling techniques, this doesn't do the collaboration any sort of justice. We learned to work over Zoom way before Zoom was a thing. Our first meeting in Tucson, Arizona, the president of Zoom came to attend our Zoom connection with the South Pole, okay? So that's how early we adopted virtual collaboration techniques. Now we are all experts in it because of the pandemic, thank you. But we had to work across different time zones. We had to work with instrumentation that you can't get to most of the year, and you have to rely on the local experts there. We had to work on comparing our analysis tools. You try this, I try this, and then let's compare the results when we were in different parts of the world. So we built this over time. And since, again, this is from a collaboration meeting in the Netherlands in 2018, as we were getting ready to publish our first sort of results. But I'm going to show you also a little video of the many faces of EHD who can never be all in the same place at the same time. So just at least as an acknowledgement of all the graduate students, all the telescope operators, all the different expertise that went into making this happen, we made this little video of what it took to image black holes. Building the models and the analysis tools is the third direction that I would like to take. And this is for the computer geeks in the audience mostly, but hopefully everybody will enjoy it. When I started doing this about, 20 years ago, and then really building these sophisticated computer models, there wasn't enough computing power to even get one series of images from this hot swirling plasma around the black hole that obeyed laws of general relativity, and you had to follow where that light went, and you had to follow where the gas went. So as we started building these more complex models, think of like these climate models that we are doing for the Earth, but around the black hole and under different conditions, computing power wasn't enough. So what we did, again, pushing the technology to where it needs to go at the time that it needs to go. We were one of the earliest adopters of GPU technology, these graphics processor units, for solving physics problems. Graphics processor units, as you know, now we have it on our phones, and every computer has it, etc. They are optimized for gaming. They're optimized for image rendition. There are many, many parallel threads where you can, if you wave your hands, for example, it will process that, and that's how you can play on your Xbox or whatever. We started solving Einstein's equations on GPUs because, again, these many parallel threads meant that here is what we could do. This is a remote control device, a leap motion. A single GPU with all its parallel threads could solve for, this is my former student who became a research member in the group. You can control what your simulation is doing, millions of photons, millions of light rays, all at once. Okay, yeah, you're not solving where did my hand go, you're solving Einstein's equations, but it's the same principle if you adopt the technology to your needs. So we were able to do these very first long and exploration simulations of black holes and really look at what that looked like, what it would look like to telescopes if and when we obtained the data. So this is back in 2012, what I'm showing you. And over the years, we have built many libraries as a collaboration of all the knowns and unknowns of the conditions around black holes. So we looked at, this is from our series of papers earlier this year, in 2022. Do I know anything about what the magnetic field looks like around the black hole? If I don't, I have to account for every possibility. Am I sure of how the electrons get heated around black holes? If I don't, I have to account for every possibility. This is why we explored not just the physics that we could solve from first principles, but things we couldn't solve from first principles with all of these different types of simulations that allowed for these different explorations. So I will show you the simulation library of what we ended up with. What you're going to see is that no matter what we did to the black holes, in almost all cases, there was a ring of light that was surrounding that heart of darkness. No matter what we changed about the black hole, as long as it was the right type of black hole and the right wavelength of light, as you can see, we ran millions of simulations, broke all sorts of supercomputing records in the United States, both in terms of weekly usage and in terms of the large projects, as we got ready to interpret what we were seeing and really understand the results. So one of the interesting things we did was ask, what if Einstein's theory is wrong? this is where pushing the frontiers of physics comes. If you want to prove that a theory works, you work in the space of alternatives, and you ask, what happens when it's not right? Do I see something different? And as you can see, we solved for all sorts of crazy and not so crazy ideas out there that come from quantum gravity, that come from string theory, that come from many extensions of general relativity that many physicists around the world are working on as alternatives to Einstein's theory. And what we showed is that there's always a ring around a hole, except for some really out there ideas. And the size and shape of this changes if you change your underlying theory in a way that is different than just changing the parameters of your flow. Using this, we were able to reconstruct images with different parameters. I just want to show you all of these different possibilities that we accounted for. Again, if you're going to make a claim, you really need to be sure that your analysis tools are not affecting the outcome of what you're showing. So what we showed is that every different way that we reconstructed the image, we were able to get the main features, like its size and shape, right. But sometimes the brightness distribution along this ring would differ by making different algorithmic choices. So we have these simulation libraries that show us size is an indicator of the underlying theory, and we have all of these image reconstruction techniques that allow us to measure the size. Let's combine these, which is what we did for both of our black holes. We measured the size of the bright ring. We used that simulation library to calibrate it. And what you see here on the right is the answer to, is GR the correct theory of gravity? Is GR the correct description of the universe that we live in? And the fact that that band is centered around 0 basically tells us now that we don't have any evidence that this theory is failing. We'll keep looking. Pushing the frontiers, going to the edge is a game like this. Maybe some other type of observation we can do, looking at how this image changes, looking at it in one other wavelength of light, will start giving us different clues. But right now, what we can say is that going to an extreme environment, like that point of no return around a black hole, it looks like the theory of general relativity is still providing the correct description of gravity in our universe. Okay, so I will leave up these two images of M87 on the right and Sagittarius A star, our beloved black hole, on the left, and take questions. Thank you very much.
I have goosebumps. So thank you very much, Feryal, for this fascinating talk and the science discovery, I would say. And it is fantastic perseverance to work on a topic 20 years also personally, you know, that you're going to solve it. It's amazing to believe in that. So the floor is open for questions, and you know now there are mics, so please go ahead.
Hi, Feryal. Thanks for the amazing talk. So I have two questions. The first one is, like, you mentioned there are several types of black holes, and some of them you can image, and some of them you cannot. So which is the kind that you can, and the one you cannot?
That's a very good question. The black hole itself is the same, but the environment that it's embedded in determines the observable characteristics of black holes. When we look at black holes earlier in the universe, when the universe is growing, stars and the galaxies are forming, and there's a lot of activity, the black holes at the centers of these galaxies also gobble up a lot of gas all at once. So these are the quasars that we refer to. And when they are eating so much all at once, all of this gas is falling in, they are extremely bright, and the flow around it looks a little less like a torus and looks a little more like a pancake. Those are not appropriate for imaging with the techniques that we have developed. It would take a different type of observation to see down to the event horizon, and it would depend a little bit more on the geometry with which you're looking. But the black holes around us actually are eating very, very slowly. It's because the activity in the universe, especially in the galaxies nearby, isn't that high. There's certainly still stars forming, gas clouds falling in, but it is at a low level that allows us to hit that right spot between it's not too bright, it's not too dim, it is just right for this experiment. That's what I was referring to.
Thank you.
Yeah.
And the second question will be I saw in one of the plots you show the candidates of stars, you were showing M31. So will we be watching Andromeda black hole anytime?
So we are imaging all of those black holes. I'm not going to go back to that now, but when we do an observing campaign, which tends to be between the end of March and early April because of good weather, pretty much on all, historically good weather on all locations and good visibility, we actually look at other targets. We don't just look at Sagittarius A and M87. So at least 5 or 6 more on that plot that I showed, we observe regularly. However, the resolution isn't enough. They are a little bit smaller in terms of black holes or too far away. So the combination of size and distance doesn't allow us to resolve all the way down to the shadow. That's why we talk about these 2 more.
Thank you.
Yeah.
Dr. Feryal, thank you for the talk. I have a question about black holes. So as I understand it, black holes are just collapsed stars. Could you please explain the physics of what happens there, and then how does this relate to wormholes, which to me is still, I'm still confused.
Sure. Short answer to the physics of what happens after the collapse is we don't know. When you create something, so let me rewind. It is true that black holes form from collapsed stars. That's the pathway in which nature can form these objects. So when stars are alive, they're generating energy through nuclear fusion, and that pressure holds them up. Once they run out of fuel, very large stars, much larger than our sun, start shrinking, and nothing stops that collapse. And they just keep on collapsing onto themselves until there is an infinite amount of energy, infinite amount of infinite energy density, basically in a single point in space-time, just like the Big Bang. And that creates this type of disconnectedness from the rest of the universe, where the energy density is so high that there is a horizon around it, and anything that crosses that horizon cannot come back out, including light. So we don't know what happens. I mean, that's what our theory tells us. But one of our reasons for looking at these objects and looking at alternatives to theory of general relativity is, frankly, we feel uncomfortable with a physical theory that predicts a singularity, an infinite of anything. In physics, we tend to think something must be happening to prevent this. But it doesn't seem to be. As far as we know, there's really a region, a singularity, a point of infinite energy density, and that's what's causing this horizon and this shadow to appear in the image. One of the things that we look at in theoretical physics today is this discrepancy between the description of the quantum world and the description of gravity at these large scales. We can't really mesh them together just yet. and we're hoping for little clues around black holes, which we haven't seen so far. Wormholes are a whole different concept. We don't think they happen in nature. They are another mathematical solution to theory of general relativity, but one that doesn't respect causality, etc. So we don't think they actually happen.
Thank you.
Mm-hmm.
Hello, I'm very impressed by your work. And sorry, what's your advice or your encouraging words for physicists and scientists? Because sometimes it can be so stressful, and I mean, at some point you say, "What am I doing?" Like,
yeah. Okay. I have a few nuggets of advice. Maybe it will work for you, maybe it won't. But what worked for me was always thinking back to the joy of what I like from day to day, not just the end result. Like, obviously, we all want to finish our project. We all want to discover something new. We all want to get to that material that we want to create, or that new DNA repair that we want to do, or this new astronomical observation. But enjoying the really day-to-day of things as much as you can, and finding continued excitement about it without thinking about the outcome is one thing that I would say. The second thing is, I like having at least 2 projects, one that is longer term and one that is shorter term. Maybe when you're a PhD student, this is a little bit harder because your project is all-consuming. But maybe in later stages, once you're a postdoc or later, always having things that have a smaller time scale, that when there is a lull in your big project or some kind of obstacle, you can always balance it out with some results, more immediate results that give you pleasure. That is one technique that I have found. And then having a good network of people around you. These are collaborators, friends, people who you can consult when things are going well or not going well, and when it's really not going well, pull you out of it and say, hey, it's okay, take a break, let's go hiking, and you'll go back to it once the weekend is over. So I think those are things that build resilience and hopefully keep you going forward as a scientist.
Thank you.
Yeah.
Thank you very much for your talk. My question was about how the rotation of the Earth can help with the interferometry, because I would imagine that the parallax between being on one side of the Earth and the other, and how the same telescope would essentially get the same image as the parallax is too small for any difference. So how does that rotation influence that? And my second question is, how do you think that interferometry can be expanded into the future with, for example, satellites placed in orbit around the sun to get resolutions as wide as the sun or bigger, and how do you think that the future of interferometry would be?
Very good questions. So the first one, how does the rotation of the Earth help? It is not the parallax effect that we are interested in. The parallax effect helps us when the Earth is on one side of its orbit around the sun versus the other. That's enough of a distance, 6 months apart, to get a parallax effect. But we're conducting our observations over the course of 10 days, basically. So what we're basically relying on is the fact that when I have a pair of telescopes and I'm looking at an image in the sky, the projection onto this is different than the projection onto this, is different than the projection onto this. So the baselines, the 2 telescopes in the pair, are literally rotating with respect to that image. So I'm getting a different orientation and a slightly different, so the projection also changes in length a little bit, but it's really the orientation that changes, and that helps you fill in the parts of the image from a different point of view. Okay? So not parallax, it's really a projection effect that you're relying on. The second part of your question is, can we use interferometry and do it in space? Well, we already are. Not for the Event Horizon Telescope, but there are interferometers that are already operational in space, and there are more that are being planned. For example, LISA is going to be a gravitational wave detector in space that is an interferometer, just like the one on Earth, the LIGO experiment, except it's going to rely on 2 satellites talking to each other and obtaining data, and very much along the lines of what I described, getting interferometric information. For the Event Horizon Telescope, we are thinking about, can we do better? Can we either improve the resolution or improve the quality of the image by putting more satellites? So if we put satellites in low Earth orbit, basically just above the Earth's atmosphere, let's say 500 kilometers, the advantage you would have is that you wouldn't have to wait for the Earth to rotate. The satellite would cover that space a lot faster. So if you put a swarm of telescopes in low Earth orbit, you could cover that image beautifully and faster. So even our best night, what I showed you, you can see there are holes. It's like Swiss cheese. So you could do that. But it wouldn't help you with resolution because the additional 500 kilometers you get compared to the diameter of the Earth is nothing. If you wanted resolution, then we would have to put telescopes closer to the moon. So maybe a third of the distance to the moon, and have them work with each other and with the telescopes on Earth. And we are working on it, but the data volume is probably apart from having to make sub-millimeter dishes and launch them to space and have them talk to one another, etc., those are a little easier to solve, but we gather about 1 petabyte of data a night because of those, the fidelity with which we have to record the signal, time-tagged. It's 1 petabyte a night. So obviously the downlink or processing would be a problem, which, next 20 years, we'll solve it.
Thank you very much.
Yeah.
Hello.
Hi.
I have 2 questions.
Mm-hmm.
So the first one is, how does it feel to have accomplished something like this, especially after 20 years, right? And the second one is, what are the new paths that such an achievement have opened, and what's next?
How does it feel? It feels wonderful for a while. The recognition that it worked, like I said, that you just see that ringing data and you're like, it worked. And I think just being able to share what we did after so long, that still gives me a lot of joy. And encouraging all of you, maybe it won't take 20 years, maybe it will take 2, maybe it will take 5, maybe it will take 20, what you're trying to achieve. Just being able to communicate to all of you, you can do it. Just go after the right tools, don't give up. All of us fail, look at the next stage. All of that gives me joy, but human nature is a little strange. I think, at least my nature. I don't want to talk about human nature. I tend to move on fairly quickly, like, okay, we did that. What's next, kind of thing. So I'm thinking about new directions now, and some along these lines, but how we can use data science a little bit smarter in order to do this type of imaging and understanding plasmas, and how we can use computer technologies. Okay, we brought GPUs in, that served its wonderful purpose. What is next? Because there is still a gap between what we can simulate and what we want to understand. So that's next for me. But also these space interferometry concepts, there's a lot cooking. But yeah, I think I'll be busy for a little bit longer.
Thank you.
Hello, Dr. Ozel. First of all, I would like to congratulate you on such an amazing discovery.
Thank you.
Do hope to see more and more astonishing discoveries from you and the team. Now, my question is regarding Hawking radiation. So as I understand, we have not yet been able to experimentally validate the existence of Hawking radiation. So can you shed a little light about it, and how would we go about discovering such a phenomenon?
Yeah, Hawking radiation is the process by which black holes can actually lose energy. It's a quantum process where pairs that are being created near the horizon, if one of them escapes, then it can technically extract energy from the black hole into its surroundings. It is a very slow process. So the amount of energy that's being generated by it for the types of black holes that we're looking at is minuscule compared to the amount of light that is generated from matter that is on its way to the black hole. So it is completely dwarfed. There is very little chance that if there is any activity around the black hole at all, that we would be able to detect and discern, like say this comes from Hawking radiation as opposed to something else. Theoretically, it makes sense, but in terms of experimental results, I think something maybe that is more likely is if there are processes that are changing the space-time around the black hole, that will manifest itself in changes in the image over time. And they can happen at different time scales. So some can be rapid. If we can obtain our images with shorter observations, maybe we will see that dynamics of the space-time, or by repeating our observations over different years and looking at particular types of changes that come from those theories where the black hole space-time changes, maybe that's going to be more likely in the near future than Hawking radiation.
Yeah. Thank you so much, Dr. Ozel.
Yeah.
Last question. Yeah.
Thank you for your presentation. I have two questions, easy ones. The first one is, what do you think, are there any practical implications of studying black holes? I mean, what would you say to the people who would say, like, why do we even care about black holes? Like, we have enough problems like here. So what would you say to them? And the second question is...
That's the easy question?
No, easy question is, do you think aliens exist?
Do I think aliens exist?
Yes, yes.
Okay, two super easy questions. Well, to people who say, what is the practical application? You can look at a lot of space exploration and find new technologies that have been developed in order to achieve that space exploration, or in order to achieve that new discovery in our universe. I mean, the space program developed hundreds of things that are household items now. But the truth is, that's not why we do it. We do it because we're curious. We do it because we're explorers. Humans have always been explorers. We always wanted to go to that edge and see what is beyond it. And I think a lot of us want to understand how the universe we all live in works. Like, why are we here? How did it form? How does it connect to... So here, black holes are a gateway to understanding how gravity works as a whole, and gravity is the glue that holds the universe together. I mean, it's expanding, but the reason why any star has ever formed, why our sun formed, why the Earth formed, is because there's gravity acting as that glue, bringing things together. So I think we just want to understand because we're curious as people. But if you really want to think about, did it pay off as far as changing how we live or changing the technology that we use? Well, even this plasma exploration that we're working on now, it might have impacts on understanding fusion on Earth. Is it guaranteed? No, absolutely not guaranteed. But the more you understand how plasmas behave and you do these sophisticated computer simulations, the more there's a chance you will understand how plasmas in tokamaks behave, or in, in the NIF behaves, and maybe have an impact there too. That's not why I'm doing it, to be honest with you. Regarding life in the universe, I like to make a distinction between life in the universe and aliens. We tend to think of aliens as civilizations who have come to visit us. I don't think that has happened. There is no evidence that any other civilization has come to Earth or sent a signal to Earth and made their presence known. So aliens per se, I don't think exist. How about life in the universe? I don't see any reason why it wouldn't. We up to now know about 6,000 other planets around nearby stars, and we can literally see a volume that's this big, and the universe is, even the visible universe is extremely large, 13 and change billion light years. So if we've shown the existence of 6,000 planets that we have characterized just in the past decade, and we basically see that there are billions of stars in every galaxy, there seems to be a planet or more around every star or most stars, why wouldn't there be? Why wouldn't life meet appropriate conditions to happen elsewhere in the universe? I mean, yes, we are special as humans, but not that special, right? I mean, we have to come to terms with that. So I think as our telescopes improve with JWST, we are now starting to get spectral information from the atmospheres of other planets, slowly. So with JWST and the next set of telescopes, we will look for signs of life elsewhere. And I would bet money, if you're asking me, that we will find life at some point elsewhere. They may not look like us, but it'll be a life form. Yeah.
Thank you very much for all the questions, and Feryal once again.
Thank you.
Have a good evening, and see you all tomorrow for the closing.